Hello everybody. Today I'm going to be doing a video where we talk about finding from the graph of the derivative the following things. We want to find intervals where the function is increasing and decreasing, describe intervals of concavity, local extrema, as in local mins and local maxes, x-coordinates for points of inflection, and we want to sketch a possible graph of the function. A couple rules first. First rule. When f prime of x is positive, f of x is increasing. And the second rule is a converse. F prime of x is negative, f of x is decreasing. The third rule that we went over, or we should go over, is when f prime of x is increasing, that forces f, the second derivative, to be positive. And when f prime of x is decreasing, f prime prime of x is negative. So the proposed plan is whenever the AP or whenever anyone is trying to evaluate your ability to handle a derivative graph, we want to first take advantage of the fact that we can take this derivative graph information and compress it into a number line. And that's the central focus of what we want to do today. So what I have is just a generic function that I drew. And I want to basically construct from the derivative graph just a derivative number line. This is very, very easy to do because all the information is right here. So what we're going to do is we're going to just analyze this graph, and we want to find out where f prime is 0. Well, here's a 0. I'm going to change the ink of the pen. Here's a 0. Here's a 0. So right there on the number line, we would like to put a 0 value and a 0 value for the derivative. You can see that the derivative is positive right here, so I'm going to just label this as being positive, and then in this region right here the derivative value is negative because it's below the x-axis, so I'm going to put a negative there. Here it is above the x-axis, so I'm going to put a positive. So what you can basically infer from this is where the derivative is positive, we're increasing, f is increasing, f is decreasing, and f is increasing again. The next number line I'm going to construct will deal with the second derivative. I'm just going to change the color of the ink for the second derivative, and that will be, I'll put x and f prime prime of x. So this number line right here is the second derivative, and this number line right here is the first derivative. So this is how we do this part. Remember that rule we talked about before. We said that if the derivative is going down, the second derivative must be negative. And that is a direct indication, or directly that tells us that f must be, you guessed it, concave down. If f prime of x is going up, f prime prime has got to be, the second derivative has got to be positive. And that means that f on that same interval must be concave up. So we're just going to take that rich source of information, that derivative graph, and we're going to construct its number line values. For instance, in this region from 1 to 3.5, the derivative is dropping. So right here at 3.5, I'm going to put a 0 value, and you can also note that the derivative graph has horizontal slope, so that's where the second derivative would be 0. So in the region from 1 to 3.5, the second derivative has got to be negative because the derivative graph is dropping. From 3.5 up until about, it looks like I marked a point here at about 7. At 7, the second derivative has got to be 0. But from 3.5 to 7, the derivative graph was increasing, so the second derivative has got to be positive. That would indicate a region where it's concave up. And on the last portion, since it's dropping, that would be a second derivative negative. That would indicate that the function is concave down. So I'm just going to write a little note here in blue about the function. So I'm going to draw in blue. I'm going to write a little summary note here that on this interval, the function is concave down. On this interval, the function is concave up. And on this interval, it's concave down again. So now comes the task of writing out those answers to the questions at the beginning. So I'm going to pause the video and I'm going to write down what the answers are for A through D, because I want to save the rest of the video to show you how I sketch it. Okay, well, hopefully you had a chance to figure all that out. I just came back from the pause and I happened to write down all the information to save you time. So the first question that we were asked in this, or that we may be asked, is on what intervals is the function increasing or decreasing? And simply, once you take the derivative graph and you construct your number line for the derivative, you can just look at the signs of the first derivative number line and you can tell where the function is increasing or decreasing. So we look at the function is increasing in the interval from 1 to 2, and then again from 5 to 8, because that's where the first derivative is positive. It's decreasing in the interval from 2 to 5, because that's where the derivative is negative. Then we look at concave up. Concavity can be seen where a concave up region is where the derivative is increasing. So wherever the derivative increases, that means the second derivative had to be positive. And that would be in the region from 3.5 to 7. And then wherever the derivative is decreasing, that means that the function, the second derivative would be negative, and that's in these regions from 1 to 3.5 and from 7 to 8. So that's what that note says there. A relative max and a relative min are found looking at where the derivative equals 0 and analyzing the sign where the derivative would equal 0 or not exist. That would be our critical points. So looking at our graph here, we have a relative max at x equals 2 because the derivative changes sign from positive to negative, and we have a relative min at x equals 5 because that's where derivative changes sign from negative to positive. And our points of inflection, they happen at our hypercritical points. Let me just zoom out so you can see this a little bit better. Our hypercritical points are the possible points are wherever the second derivative equals 0, and you can just look at the sign change, and that would indicate when a function changes, second derivative changes from negative to positive, we're changing from concave down to concave up. So we have a point of inflection at 3.5, which is here, and at 7, which is here, because the concavity changes. Now let's learn how to use our derivative graph, derivative number line, and our second derivative number line to construct the graph of the function, because the last part of this problem says construct the graph of the function. So at first we just use the derivative graph and we just simply draw, start it, because this can be any graph, I'm just going to start right here at x equals 1. That's where my function will start. Looking at my number line graph, I see that I have a positive derivative, so I'm just going to be increasing up until 2, where I have a 0 derivative. So that's where I make a flat line for a 0 slope, and then I'm going to be decreasing up until 5. So I'm just going to draw a line that decreases. Now notice, a line has no curvature, so I haven't added the curvature in yet, and that's where I have a 0 derivative, and then it's going to from here increase again for the rest of the graph, because this region here says it just increases. So I've got a line that indicates increasing, decreasing, then increasing again. Now I'm going to add my curvature, and for that I'm going to use the color green. As I said before, green would be dealing with my second derivative. And if you look, in this region here, I have a concave down region. So I'm going to just draw, remember, concave down makes a frown, up until about 3.5. And that would be my point of inflection, because I'm changing from concavity. Concave down, I'm going to change to being concave up. And notice how I add the curvature to this graph, which didn't have curvature before, but now I'm adding it in. And now I'm going to just put my inflection point here at 7, because I see I have a change in concavity from positive to negative. And now I'm just going to make it turn around and have downward concavity. And that's how you construct a possible graph, a possible function graph from a derivative graph. Foolproof. Well, hopefully you enjoyed this video and you liked this video and subscribe to this channel.